this morning session. It's a pleasure that Fabrizio Bianchi from the University of Pisa is going to speak about all maps of semi-parabolic Hénon maps.
Thank you very much. So first of all, let me thank the organizer for the invitation. It's always a pleasure to be in Poland and in Bedlewo especially. And so I'm going to talk about a recent joint work with Mathieu Astor from Orléans. And it will be about the generalization of a result in one dimension to two dimension. So I will try to spend a lot of time actually on the explanation of this result in one dimension first. And then I will give the ideas of what's different and what has to be done in two dimensions. So in order to start, I will consider f from C to C a polynomial. Or you can take a rational map, it's the same. Here, as it was already introduced, for a polynomial, let me define K as a set of points with bounded orbit. And the Julia set as the boundary of this set, which is, of course, the non-normality locus of the sequence Fn, which is the chaotic part of the system. Now, as it was already said many times, and this set is also the closure of the set of repelling periodic points. So what I would like to say right away is that this equality, as it has already been said, it's not immediate or clear a priori for more general families of dynamical system. It's clear in this case, but it's not clear for general map. And this talk will be about considering some class of more general map that we will see and see if this property is still true. So as an let's say example, so let's first start with the motivation, which is the following. So of course, if we take the map z goes to z square, or we take the map z square, say, plus c with a c very big, let's say real positive, the Julia set is a very different shape. In one case, is the boundary of the unit disk. In the other case, again, as it was already introduced many times, with c big, it will be a Cantor set, let's say c very big. So the question that one can ask is what happens when C goes from 0 to, well, let's say this picture, very big. So at some point you start from 0 with a parameter. What happens as C becomes big? And as it has been already again introduced many times, it's the good thing of not giving the talk the first day or 2 days. One could introduce the Mandelbrot set. Where taking all this family, z square plus c with variance c, this, for example, is a set of parameters c for which the Julia set of the map, let's say, at parameter c is connected. I could use the field Julia set, it's the same. And so the boundary of this set is equal. This is a theorem, it's not a definition, so this is a theorem. Is a set of parameters C, where the map C goes to J of C is not Hausdorff continuous. I will not enter in the detail of what this precise definition means, but in practice, it means that from here to here, something happens. And so it's a way to say that as a parameter goes to the boundary of the Mandelbrot set, it's not true that the Julia set at the limit and the Julia set of the small perturbation are close to each other up to an epsilon error. This is what it is. So, an example of parameter here, so an example of C inside the boundary of the Mandelbrot set are parameter C such that there exists a parabolic fixed or periodic point more on this later of what happens. And so I can think of them as actually they're the parameter with this parabolic periodic point are dense in the boundary of the Mandelbrot set. And the theory of parabolic implosion is essentially a set of techniques and result to study perturbation of these parameters here, okay, parameters with a parabolic point, in order to get information not only, for example, of the discontinuity, but also to estimate at which point we don't have the discontinuity, okay? To give a maybe more quantitative way of studying the discontinuity here. So, of course, as an example, if I draw the Mandelbrot set, I mean, or at least a very Hausdorff close approximation, and if I, for example, take this parameter here, has already been studied in previous talks, and I take a sequence of parameter approaching this from, not necessarily from outside actually, but let's say from this direction. And so this is 0. This is the parameter corresponding to z squared plus 1/4. So this parameter here, one can check I have a parabolic fixed point. And the idea is that if we can understand precisely what happens in this neighborhood here, then it's essentially the picture that we will find everywhere else in the yes.
Boundary? Where is it?
Thank you. No, not necessary.
In a neighborhood, sorry, I should say in a neighborhood. So I take in a neighborhood of C, so you don't need it. Yes. Thank you. Yes, I think of this as an open condition, so it's in a neighborhood. Or you take the closure if you think of pointwise. Thank you. So I was saying we want to understand what happens here precisely, because if you understand precisely what happens for the perturbation of this parabolic map, then it's essentially the same picture, will be more technical, much more technical, but in other all the other points with the parabolic perturbation. And as it was already said, copies of Mandelbrot set are dense in the Mandelbrot set, so parameter like this will be again found as dense in the Mandelbrot set. So it will have to explain the discontinuity everywhere. So, for example, one of the things that one can get with the theory of parabolic implosion is, for example, as a consequence of this theory, one can get an estimate for the size of the boundary of the Mandelbrot set. It is a theorem by Shishikura that the Hausdorff dimension of the boundary of the Mandelbrot set is equal to 2. So this set is as complicated as possible in some sense, of course, and it does not contain open sets. So this gives importance to this result. And I would like to say how this theorem is proved. If I have to say it in one line, the idea is to say that if I take this map here, for example, let me call it F1/4, the Hausdorff dimension of the Julia set of the map, let's say z square plus 1/4 plus, let's say, epsilon square with a well-chosen perturbation like this. This Hausdorff dimension tends to 2. Tends, I mean, up to subsequences, whatever, tends to 2 as epsilon tends to 0. I should take subsequence. But the idea is that I have hyperbolic maps near my parabolic map with a very big Julia set. And then there is a transfer phenomenon that permits to take this and send it in the parameter space, and then recover a big set of bifurcation, which is inside the Mandelbrot set. So this is really the key, okay? To use parabolic maps and the control that parabolic implosion gives us to construct other hyperbolic maps with a big Hausdorff dimension for the Julia set, which will give a big Hausdorff dimension for the Mandelbrot set, okay? So this is really the key to give this. Okay, so let me say a bit more what's the dynamics of this parabolic point? Why we can, why they are a good type of map to study if you want to understand this chaotic behavior for perturbation. So let's study a bit more parabolic fixed point. I will consider here the map z plus z square for simplicity. One can see that actually up to a linear change of variable is conjugated to this one. So it's just because it's simpler. Because in this coordinate, I can use this and the perturbation plus epsilon square. Okay, think of epsilon positive, okay, real positive if you want, or for now. So the map, the dynamics here of this map, if I start from the real axis, I see that I have on the right-hand side, I have the identity plus another 10, which is positive. So it has to be like this, because it's the identity plus a positive part. On the negative part is the identity plus a positive part. So the parabolic point is playing the role of both an attracting and a repelling point. Now, I could draw a picture of the set of points which are attracting to this point here. And actually, all the convergence happen tangentially to this real axis. Okay? Now, this is, in this case, the field Julia set. On the other direction, or if you want, considering the inverse locally of this map, I could see that all orbits escape also tangentially from this point here, real to the real direction. When I do this picture, I could also, as sometimes is done, picture like something like this, which we call a petal. Let me just notice that this picture of petal is not canonic at all. The only thing canonical here is the Julia set. It's not a canonical definition of what is this petal. So now, what happens if I perturb my map? If I perturb in this way, as I said, let's say epsilon is real or very close to real. Now, instead of having a fixed point in 0, this was 0, of course. Now I have, you can say that the points are IE and minus IE. These are the fixed points. And as epsilon has just become positive, now points on the real axis that was here, actually they can pass through the interval that is between this point and then go away. This is a general idea in dynamics that if you have a big change of the dynamics of the critical point, it gives a big change of the dynamics of the global dynamics. Okay? In this case, the critical point is 1. The critical is 1 minus 1 over 2, which is here. So before it was attracted to this point, then this point disappears, and this point here, which is again the critical point, can go to infinity. So this is the big change that we want to exploit. Now, so if I take points here that were used now to converge here, now orbits can go away and go away like this. We'll go back now in a moment to this picture. But the theorem, which is the start of parabolic implosion, the theory, is the result by Laveur and essentially Douady, and but it was in the PhD of thesis of Laveur, the end of the 80s, which is the following. If I have a sequence of integers and the sequence of epsilon satisfying these properties, goes to some alpha in C, you can take 0 for simplicity, okay? It means just that you have some epsilon going to 0 and n has to go to infinity, like essentially the inverse of this, with there is pi, but it's not very important. Then on B, which is this basin, I didn't write, I will write next time. Then you have that F epsilon j, so the perturbation, and j converge locally uniformly to a map T that depends on alpha. This is called sometimes transition map or Laveur map. And now, let me just say this gives the discontinuity of Julia set. I will not enter in this because we will say something more than this, actually the estimate of how much the discontinuity is big. So we'll see later the precise part. And so this is called the Laveur or transition map. But the idea just in 1 second is that suppose that you have your Julia set. Now I take a region here. And I have this convergence here at the limit. Now, alpha, I have a degree of freedom. So I can essentially make T alpha go where I want. I could say, for example, make choose alpha in a way that now, for big iterate, the image of this ball goes close to here, for example, by T alpha. Now it means that pre-images of point in the Julia set by the small perturbation of this, which is this big iterate, also have to be here. So for a perturbation of my map, I will find point of the Julia set here. If I can make this convergence very precise, I can estimate how much part of Julia set I put here and estimate the Hausdorff dimension. So this is really the idea. But in order to see how it works better, let me say what it is this map actually, precisely. Because, for example, I use the fact that if I vary alpha, I can move the image of this map, which is not a priori. I have to tell you what is this map. So to define this map, as I said there, I say that if you have a parabolic point, you have your orbit of points converging here, and you have points going away. I said you have a basin here where you have the convergence, and the basin where things go away. Now, as you can do for attracting point, you can almost linearize the dynamic here, in the sense that there exists a map phi, I call it with I in the sense of incoming, that goes to C, that semi-conjugates my dynamic F. This is really the dynamics at the limit, so F, to a translation by 1. Okay? This is semi-conjugation. It's not a conjugation because you have a critical point, so it's not really invertible. So this map, it's sent to a translation by 1. At the same time, here I can take again the translation by 1. And I have a map now that I will call psi outgoing. Now it's well defined in the other direction. That sends the translation by 1 to the iteration of F. Okay, so on both sides, I have two maps that think in some sense that conjugate. It's not really the important point of the semi-conjugate. This iteration by F becomes the translation by 1, and similar on this side. But now you can realize that this C and this C actually are, there is one C. Actually, so you can say I can also compose here with the translation by alpha on C. And so I can define my map, T alpha, which is actually the map that goes phi like this. I compose by this T alpha, which is the translation by alpha. And I go back to the phase space with my map here. So now you see I have an open map here, a map for which with the one-dimensional degree of freedom that in practice is a translation. And then I go back with psi. So here, if I move alpha, now you can believe me that this ball will move around. Okay, so this is really the degree of freedom. And it's important that it is complex and not only real, because I want to be able to cover a large part of the Julia set. If it was only real, I would only be able to move the ball in this direction. It is not clear it would be helpful. So this is the map. And so this map, so it's defined from B to C. It's not to the basin a priori, because I can put any alpha, and then it will go anywhere. Now, in the rest of the talk, for simplicity, I'm just going to consider the case alpha equals 0. Okay, so I will not take a translation here. I will just take alpha equals 0. But what I'm saying, it's the same if you take alpha different from 0. It's just that it's a bit more complicated to write down. So now, so take alpha for simplicity equal to 0. Now, here we say, okay, this pair of maps is conjugating my dynamic F in some sense to translation. Now, let me define this map H of alpha, H of 0, which is the opposite. It takes psi 0 and compose with phi. What is this map? So I first take the map from the abstract C and go to the petal here. Okay, and then if I have defined this from, let's say, C minus 1 of B, once I apply the first map, I go in the domain where I can apply phi. I apply and I go again back to C. So it's from a subset of C, okay, where I will be able to iterate, to the set C. I won't think of this now. It is completely on the abstract space. So this is not the dynamical space. It's really all in this abstract space here. And the important point of this map is that since I have two semi-conjugation of +1 with F, now this map commutes with the translation pi 1. Because they cancel each other here with F. So if you have a map on a subset of C with commutes by +1, let's say it's defined on something like this. So it's defined on this part and on this part of C. Because in this map, you see here I have the Julia set. So I have to imagine C that is sent here. So it's like the preimage of this part and this part. So which are like two parts up and down. It commutes by +1. So since it commutes, I can take this one. It goes, I can see it as a map on a cylinder. On the ends of a C. Okay? It commutes by +1, so I can see it quotient a translation. Now, the first point that happens is that actually I can extend this map. It's not obvious, but it's possible. I can extend this to both extremities of the cylinder. Okay? With two fixed points. So I extend, and now I get a map from the Riemann sphere, from a subset of the Riemann sphere to itself. So this is the domain, it's not the image. The image is a priori all the sphere. So this point is fixed, this point is fixed, and I have this map here. And I have a map, I will call it H, from U to P1 or C hat, if you want, let's call it like this. This is what is called the Horn map. I could put the parameter alpha, so I have a parameter. But if you want, the idea here is that, for example, taking the basin here I said I have the orbit going away. I have a fundamental domain which has this shape, which is sent in another fundamental domain like this. I'm taking just one of them, okay? And they have this set of definition, which is just the up and the lower part. I'm adding here as compactification 2 points, as if it is a sphere. And then I'm seeing the dynamics of what happens iterating sometimes, come back and do the translation. This quotient by +1, it's a way to say I don't care about a big number of iterations. Because I'm killing, I don't know how many iterations I'm taking. I'm just saying this map as a return map. So the idea here, since I'm taking a quotient, the idea is that H, this map H in the abstract space, so it has a dynamics of H. It's related, so essentially it describes the limit dynamics of the perturbation, let's say F epsilon J. For, let's say, Nj, with Nj P over epsilon J, okay? So this is the idea. This map is a kind of limit maps as I perturb at the same time epsilon and n in this way. And for a bit of moral idea, the idea of parabolic implosion is that in dynamical system you have two sources of error. You have the perturbation, which you make you lose control, and you have a large number of iterates for which you can lose control. All the theory of parabolic implosion says that if you compose these two sources of error together, but with a very precise condition, the number of iterates is related to the perturbation in this way, then actually you gain control. And in very strong sense. If you want to guess why Nj should be this pi over j, if you go back to this picture here, and if I take the multiplier here, what is the derivative? It is 1 plus 2z. So if I take it at the fixed point, it's this one. And you see that this is 1 plus 2i epsilon. It's a point which is more or less here, okay? If you see now a point here, how much time it takes to essentially rotate now, because it's a very small rotation now. It's expanding, but very small. What's the rotation number of this? It is essentially pi over epsilon. So the number of iterates you want to take to come back, if you want, must be comparable to pi over epsilon, because the rotation number is this. Now here, we take 1 because we want to go from here to here and not come back, otherwise you will have a 2. But this is really the idea. Okay, so now we understand, I hope, that in order to study not my map F0, but the limit of the perturbation of F0, which means the limit of the dynamics of F epsilon, which we know it's not F0, this is all the standing assumption, we can take this limit in this way, take this map, and this map describes the limit of F epsilon, okay? So this is the idea. Limit of F epsilon is not F0, but this is this map H, okay? This describes the limit of the perturbation. So this map H, as I said, lives acts on a subset of P1. Sure.
Square plus 1/4 has Hausdorff dimension equal to 2.
No. This is the point. You want to find perturbation for which the Hausdorff dimension becomes very big. It's yes. It's, so yes, you want to find the complexity real by perturbing, and the small perturbation will add decoration. Now you send the perturbation to 0, but in a way that you keep the decoration, and actually they become more and more. In the limit, you will get the Hausdorff 2. But it's really the point that the limit is not the dynamics of the limit map. So now you have a map from a subset of the Riemann sphere to the Riemann sphere. So I could define the Julia set. We are here for this. So I could define as the non-normality of the orbits with the, okay, of course, as it was already introduced with the polynomial-like maps, when they are always defined. If they stop to be defined, I say, okay, forget, it's in the Fatou set. Okay, I always say, in some sense, this, you can think of this as the boundary of this set and all the preimages of the boundary. Okay, so this is the non-normality of the orbit. And now the question is it equal to the closure of the repelling points? Which is a priori not clear. And if you can answer this question and say that the answer is yes, actually, and if you can do precisely, in the sense not only say that it's a closure of repelling point, but construct them explicitly, for example, with an iterated function system, now you can say, I can also estimate the size of the set of the limit set that I have inside. And so you can get, it can be used to measure the size of the Julia set of H, which, as we said, is the in some sense is the Julia set of the perturbation of my initial map. Okay? Yes.
Our map is basically the Labor's map if you move the translation. So forgetting the limit, all the limits for FA when you go to the parabolic points, don't you move the parameter of the Horn map because you just get for alpha equals 0.
So I'm saying, yeah, I'm just focused on alpha equals 0, and then I always use this alpha. The alpha is saying sometimes the angle at which I am arriving, but once I fix it, I don't have to move it. I can fix it once for all. I fix alpha, and it says, okay, if I come from this direction or this direction, okay, I only study this. Yes. In this case, if I take alpha 0, I'm going with the real axis, just because it's simpler with the formula, but it can be done for every alpha. But I fix alpha. It's not a variable now. It's fixed. It's fixing, yes, I'm fixing in which direction I'm arriving. Now, in this case, that I'm describing here, so dimension 1. So the answer to this closure of the repelling points is yes. And it's essentially, even if it's not explicitly done in this context, due to Adam Epstein in a more general theory. He has done a more general theory that I will mention in a moment, which contains this one and gives the closure of the repelling points. But more precisely, one could build not only a lot of repelling points, but also an iterated function system with this map. So a big set with a lot of inverse branches that I can estimate. And this gives a big hyperbolic set inside the Julia set of H. Now, this gives a Julia set for f epsilon j. This is the theorem by Shishikura, essentially. Okay, to make this construction explicit here, it's independent from the one of Epstein, but this is want to stress this one to build this iterative function system to estimate the size of this limit set.
Your semi-group action, you started with one mapping and then you obtain two generators.
Yes. Yeah. So the idea of the iterative function system is that yes, you can build
original and they commute.
Yes, you have the inverse one, you use them to build a semi-group. And the idea is that you have sufficiently good control, if you want, on the geometry of all these branches, in order to have a good control on the limit set. But yes, it's in the framework of semi-group if you want it. So, okay, so this gives also the theorem of Shishikura. Okay, why I'm here? Why I'm here? Because you can ask, Now the same question for another class of maps. I mean, you can ask in many settings, but what I'm interested now is the following. If I go to dimension 2, and I consider a map F, which is called the Hénon map. This is nothing more than a polynomial diffeomorphism of C2. So if you want to think very naively of a Hénon map, if you've never seen, think of this as a perturbation of a polynomial map, okay, which lives in C. You put in some sense on a curve in C2, and then you perturb a bit with the parameter in order to distinguish the pre-orbits, okay? Instead of having a point with the d preimages, d square preimages like this on the same curve, okay, you are perturbing a bit in a way that now all points become invertible, all the map become invertible, okay? You have all these preimages, but you added in your system, maybe here you had the Julia set here. Now you have something more like this. You have the Julia set, which is a bit perturbed like this, and you added a strong attracting direction transversally, okay? So you have expansion in the direction of the Julia set, but you have a contraction in the other. So this is the picture how to think of a Hénon map, okay? At least it's Julia set in some sense. Here you can imagine that the important points are not the repelling points, but will be the saddle points, because you have the repelling one for your polynomial. Then you perturb a bit to make the system invertible, similar to the setting of a natural extension that was already mentioned. And you are adding another attracting direction. Okay, so it makes sense to say, does this theory continue to hold in the setting of semi-parabolic Hénon maps? When I have a polynomial, for example, with a parabolic point, now I make it a Hénon map, so I add the attracting direction. Is it still true that I have this picture? So in this, what is called a semi-parabolic case, what you have is you have a point, parabolic. Now I should imagine that I have now, imagine a kind of one-dimensional petal, if I would like to think, but now it's two-dimensional. So I have a two-dimensional basin of points because it comes from the one-dimensional basin, and then I have the other attracting direction. So I have a two-dimensional set of points, which is attracting to this one. And then I have a repelling petal. This persists a bit better because it's still dimension 1, because I cannot add since I have added an attracting one. So it's a curve, it's sigma, it's a complex curve here with this point on the boundary. So here it's invariant and F sends the points away. Here it's two-dimensional and F sends the point to this point, okay? But again, as a model, think of the polynomial of dimension 1. You think of it just with an attraction in the other direction. So it's clear, now it becomes the repelling petal stays the repelling petal. The attracting one becomes a cylinder on it because you are adding the attracting direction. And now you perturb a bit to make it invertible. But globally, the picture is kind of this. Now it's a theorem of Bedford, Smiley, Ueda, 2012. And let me also mention, let's say, Dujardin, Lyubich. I think it was in 14, because they precise this construction. If I now take, let me call it maybe F, to distinguish from the dimension 1. I will not write down explicitly the formula, but it's essentially a one-dimensional polynomial perturbed with the attraction. If I take this and I perturb with a suitable way, same condition as before, pi epsilon, this goes to a map, T alpha, on B, locally uniformly, a map from this two-dimensional basin now to this one, to this sigma. And what's the point here is that now, since I have a big contraction, I cannot expect the limit map to be open. This will be one-dimensional, so 2 to 1 dimension. Okay? So it contracts. The more I do this, the more I do this, dimension on this direction is like the parabolic dimensional one, but in this direction I'm contracting, so the limit will be one dimension. So I have to say that since it's not open, it's a bit more difficult, actually more difficult to get the discontinuity of the Julia set in this setting, but it can be done. But I don't want to focus on this. So I skip this. So in this setting, one can also define here a map phi that sends to a translation by 1. I could make it go to C2, that conjugate it to a translation plus 1 and 0 in the second. But since we don't care, I just take a weaker map, which is just the first coordinate, if you want. I just go to C for simplicity. And then here I also have, as before, a map which conjugate by plus 1. So I go here and I go here. So now I have a C here. I can also have my translation by alpha if I want to put the parameter. And I can still define my Horn map H, which is CO composed phi. It goes from, let's say, C to C, where C is again the preimage of B, but it is the same as before. It's the preimage of is CO minus 1 of B. I have a part here of C, such that I go here, I enter in this basin, and now I can apply it. So the problem is still one-dimensional. So this is one-dimensional. Yes. Yes, and not where you use. But yes, here there is in some. Okay, let's do this. I have a, for example, I can take some points and orbit.
Points.
If we take a point here by this map, the preimage is the curve, which is a strong, stable manifold for this point here. The geometry of this curve can be well controlled here in the neighborhood, but it's very irregular when it goes to the boundary. This is very important. For every point here, let's say 1, 2, 4, 1, but for every point I have the corresponding preimage here. Yes. And here I don't even have the problem of critical points. So it's
Such pictures were done by Newhouse Paris Tucker.
Yes, it's all. Yes. Yes, it's not more than. No, the point here is really the map conjugated to plus 1, and this is a factor of the complex dynamics. The fact that then you complete with stable manifolds, yes, is more classical. So you can define this map, and I want to say that how Bedford-Smile-Weda can prove the discontinuity of the Julia set in this setting is by constructing essentially one saddle point for the limit map here inside this basin. One starting from one periodic point for this map. Even finding one periodic point is not clear and requires some condition, requires some work. And so there is a question, as here. A question already by Bedford, but in the same years. Let's say, is it true that the Julia set of H is the closure of the repelling points? So in their paper, they can build for some choice of F, for all F, but for some choice of alpha, they can find one periodic point and use this to find the discontinuity one. So as I didn't know, we didn't know when we did this, but at some point, Ljubich, actually during the talk, it was in Banff, asked the Bedford, is it possible to use this to construct a map F Hénon with the Hausdorff dimension of the Julia set, let me say in this way, plus close to 4. Now, why I'm saying J plus? J plus you have to imagine as this set, which is saddle type, union of its stable manifolds. Okay, so it's like a Julia set of dimension 1, union all the stable manifolds. It's a bit stronger than saying, but I could say that the Julia set of the Hausdorff dimension 2, if you want, is the same, because then you add the stable manifold of dimension 2. And this will be the tool. If you can do this and do it precisely, as the proof of Shishikura, you can estimate how big is the size, and so you get this. So the theorem that we did with Mathieu is here is that I don't rewrite, I say yes. You can do these two things. And okay, so in the negative number of minutes I have, I don't know how many. Positive. How positive? 10 minutes. In the next approximately 10 minutes, I will try to give an idea of more than the detail itself, what are the objects that in dimension 2 replace the objects that they said before in dimension 1, okay? And what are the tools that one needs to use in higher dimension to estimate this. So let me go back to a definition, which I think was not well known to me, and I think it's still much more well known to a lot of people here than it is to me, which is the property of the n islands. So I say that H has the n island property, n islands, if, let me first make a picture. So I take this H is as before. I will work on now only on this setting of the Horn map, but it's general. I can take any map from a subset of the Riemann sphere to the Riemann sphere. I take my domain like this. It's defined here and here. If for every D1, Dn, let's say Jordan domain, disjoint closure, and of course, and for every U which touches the boundary of W, let's say that W is the set where it's defined, so I take a U here, okay, for every U, there exists a I0, I0, and omega inside U and W, which means a small set here, this is W, this is omega. Suppose that I have some disks, I don't know where, they can be anywhere. So let's say this, D0, such that H from omega to D naught is a conformal automorphism. Conformal isomorphism, not very important. It could be a ramified covering. The important thing is that it's proper. But let's say conformal isomorphism. So what I'm saying is that I have from this small set here an inverse. I have an inverse branch defined here on DI naught that goes here, okay? Which has to be in some sense contracting, because if it was here and I can put U as much close as I want, it will be close. So these are, let me call it, is a good inverse branch. Something that was already introduced several times. Good inverse branch. Now, if you get this property, it's not difficult to see that this implies the existence gives the repelling points. Because now here, you could take actually, essentially, you can take U itself and find an inverse branch that goes to a subset of itself. You go back and you find an attracting point for the inverse, which is a repelling point. So once you get this definition, it's not difficult to find repelling points. And with a bit more work, you can get your iterative function system and the Hausdorff dimension. Okay? So this is the idea, dimension one. So maybe someone here is more comfortable with the notion of maps of finite type. Finite type is that the number of singular value is finite. Now this plus a condition like that the boundary is not empty, so I'm not taking all P1. This implies this definition, okay? So if you have in mind the maps of finite type, this implies this definition. It's a generalization of finite type. And so in particular for finite type maps, these properties are true, okay? The density of repelling points, and I have to ask that the boundary of the domain of definition is not empty. Yeah? And you have this one. So the work of Epstein actually was essentially in this family here, in this setting. But reading what is written, is this what is used? So this is the good assumption. Now, so Epstein also could prove that in dimension one, in the result I said before, what I erased, H has the island map. Actually, has the island map, island property. Should be like 3 island, but it's not very important, the number. The number is just there to say that there is, it can be any number, it's the same consequence. So the work of Epstein says that there is this one. So here, what we could not prove this. There are reasons, I will try to explain why. But we have a weaker property than the small island, than the island, which is still enough to prove that the consequence is good. Which in some sense adapted to the situation. So weaker property. And I just state in the case of 3 islands because it's, let's say that I still have my map, my domain here. I'd say that for every, so let's say that these are 0 and infinity, okay? 0 and infinity. So this is a C star. So for every Z naught in C star, so I remove 0 and infinity. In some sense, it's like the 3 island, but I fixed the third one will be fine. There exists an R which depends only on the point, such that for every U which touches the boundary, so now I take again as before, I take U here, okay? There exists omega inside U and W, so as before, I take an omega here. And now I have a point here and my ball R0. And such that H from omega to the disk of Z naught and radius R of Z naught is conformal automorphism. Again, I need proper, but the point is, what's the difference? But it's a weak version of the 3 island property, because it's like if I put a domain here, and the domain here, but I say a priori, okay, the one I will take is this one. I will never take this or this. This is the reason also of the 3 in Epstein, that the two to exclude are this and this a priori. But what we don't know is that it works for every domain, but for every point I have a radius which works independently on the U I will take. So this depends only on Z naught. So it's not true for every set a priori, but it does not depend on U. Whatever U I'm going to take, it's fine. I can always find a small preimage here, always for the same disk here, which is what it needed actually. One doesn't need. Once you apply, it's enough. It's so this gives, so this, same as before, gives the repelling point. So it's a kind of weak version of the 3 island property, where on the other hand, yes, you fix that the third one is the one. Roloff?
Or
So I cannot take for every set, but I say for every point I have a radius. For this set, I can have the island. Or of course, for all the ones smaller, but it's for this radius. Now, what we can show is that the theorem actually says that every semi-parabolic Hénon map as that is there, every Horn map has this property, has this weaker island property. As a consequence, gives repelling points, and you can quantify this construction to get the IFS and the estimate for the Hausdorff dimension, as I said before. So to answer the question that I raised. But so let me make the comment on what's different from the dimension 1 and maybe why we have to reduce the definition and how we do it actually, and why it took some time. What's the tool that is used which is not from dimension 1? So here, so idea of how. So the idea, forget the radius, okay? Start forgetting the radius. Just try to say, okay, I want a preimage of a point. Then we can build the radius. But you take a point, I give you, and I want to find a preimage here. Just start from this. The case of, I think it's called Casolati-Weierstrass property. This is a weaker property. So you start finding just preimages, okay? It's a weak version. What is a preimage here? In our case, a preimages, so need to find preimages. Then you quantify the radius, but what it is. Here, remember, this is a model for this map here. And as was said by Felix, what is a preimage by this one? You have to take a point here. You have to take a point, and I have to do my map, which is this and this, okay? So the preimage goes, take a point, I take a stable manifold, and then I have to take an intersection of the stable manifold with this unstable manifold here. This is my preimages. Okay? This is very long. It's a transcendental curve. It intersects this many times. All these are preimages. Okay? So the preimages of my map here, given a point, all the preimages are done in this way. I take a point, I take the stable manifold, very long. I intersect it with this other transcendental curve. All the preimages, all the intersections are the preimages. Okay? I have to find intersections. How do I find intersection between 5 preimages? Becomes intersection between stable, so strong stable manifold in B, and sigma, which is the repelling petal. Okay. So notice that this stable manifold is not the stable manifold of a point of the Julia set, for which phasing theory applies directly. It's not on the limit set. This sigma here is the sigma of a parabolic point, which is not well behaved as the repelling manifold of a repelling point, of a saddle point. So if I want to use phasing theory, so by phasing theory, I could say, okay, I have a box somewhere in my space where I have unstable and stable manifold. Okay. Now, this one, the stable manifold, maybe arrives like this. I don't know. This is a stable manifold because it's not one of the picture of one of the manifold in the phasing picture. This is a stable manifold. I have sigma like this, and I want to use this picture to find intersection between this and this. And actually, with the neighborhood of this, finding this with the neighborhood of Z0 will mean finding a tube of manifolds here. All of them will have to intersect. Now, it's essentially phasing theory that by the inclination lemma, this will tend to the stable manifold here. And this one, the other one, by the other iteration, will tend to go here. Okay, so the intersection, I can find them in this way. Once I enter in a phasing box. But there is some condition to be able to apply this. I have to make sure that there are already some intersection between this manifold here and the other stable and unstable, and some intersection between sigma and this other stable and unstable. I have to make sure that there is the intersection here with the vertical and this intersection here with the horizontal in order to apply the inclination lemma. Now, why I can make sure that I have this intersection here and this intersection here? There are results, and now it's the moment, there is pluripotential theory arriving. And so there are results that say that if I take, for example, let's call it S, an algebraic manifold inside a curve, a line, for example, and now I take the preimages of this, and I take, let's say, the integration on this surface. It's a surface. I divide by the degree of my map and n, but as objects, let's say in average, they converge to a something, which is, I take back, so it is T plus, a singular object, which is supported precisely on the set of points whose forward orbit is chaotic. Okay, this is true, but this has to be algebraic or contained in the correct Julia set, plus or minus, I have to think. Same as the other, you have Fn of S divided by the n. This tends to the another object, which characterizes a stable manifold, which again has to be algebraic or contained in the other Julia set. In this case, we have to apply this because these two intersect. These two objects intersect, is the measure of maximal entropy. So what I want to say is that, okay, I have an object that converts to this one, an object that converts to this one, and I have to say, okay, maybe in the limit they will intersect, okay, but why this, I can apply this theorem, and why this one? Knowing that we want to apply to a stable manifold which is not algebraic, and to a unstable manifold, which is an unstable manifold of a periodic point, which a priori does not apply. There are results by Bedford and Smiley on these cases, but it doesn't apply here. And this is true. And this uses the theory of, let me say, horizontal like maps of Dean, Nguyen, and Sibony. Let me say in a word what is this theory. In dimension 1 for polynomials, you have the theory of polynomial-like maps. Are maps from a big ball to a big ball that geometrically expand. They behave geometrically like a polynomial. And you can prove that they are conjugated to polynomial. This you can do in any dimension. You can take a big ball, which is sent to a big ball. You call it a polynomial-like map in any dimension. These are an infinity dimensional class. It's not true that they are conjugated to polynomial. But then you can say, okay, let me take it across maps. I take a map in dimension 2, which geometrically does this. Contracts in one direction and expands in the other one. Maybe the picture which is more clear to many of people here is if I do the picture in this way. This is a horizontal-like map. I have a set, and I send it to another set of C2 in a way that it's contracting one direction and expanding in the other one. But what happens if here is this way, is like this? That's complex. Suppose that maybe it's sent in this way. I have some parabolic point. It's not uniformly expanding. So it's a way to have a map, which is a horseshoe if you want, but not uniformly expanding. It's completely generic. You can have a parabolic point. In the same way, a polynomial-like map can have a parabolic point, can have anything. You can have a horizontal-like map, which the model will be a horseshoe, but is non-uniformly parabolic, and is any possible combination. So this is the local picture of a Hénon map in the bounded part where you have the recurring dynamics. Now, you cannot use two global tools in order to do the convergence because things are not algebraic. They will not work. But you can use semi-local tools of pluripotential theory to say that in this big box, things work in this way here. Once you can prove that in one big box, you still have a well-defined degree, a well-defined growth, you have this convergence. And now here, what replaces algebraic or a disk? The idea here for a horizontal-like map is that you have your current T plus, I said it, another current T minus. And what is true is that for every vertical object that I can take here, by taking pre-images, it will become singular. But as soon as it's vertical, in the sense the boundary goes out from the vertical direction, then it converges to T plus. We can apply here because we have a sufficiently good control geometry for the stable manifold to make them vertical. We can do for in the other direction to take the horizontal one. This one will be sigma. It's enough once it's horizontal to converge toward this current here. One is to make some checks to make these two convergence and to make sure that the intersection pass to the limit. But this is what potential theory is about. So it's done for this. Okay, so I hope at least I gave the idea. Maybe I should stop. Or okay, so I stop here and I thank you for your attention.
Any question or comment? None?
Can you say something about dimension in the parameter space? Good question.
I didn't mention because, so yes, this will give a Hausdorff dimension of parameter with some phenomena. The point is that it's not so interesting in this specific case because we know by essentially the Newhouse phenomena or this, that there are open sets in the bifurcation. So the analogous of the Mandelbrot set for Hénon maps contains open sets. So the fact of estimating the Hausdorff dimension was not a motivation. This gives the Hausdorff dimension of the parameter with some specific parabolic like, yes, this is possible. But the fact itself of doing the parametric version was not the main motivation because there are open sets in the bifurcation. But yes, it can be done, yes. It's just that it's weaker than something already known by other methods.
Some comment? Or if not, thanks, speaker again. I'm not wrong. The lunch is at 1, not at 1 and 2. It's at 1 o'clock. So half an hour.